we have mentioned that the random variables can be classified into two classes, discrete and continuous random variables. So discrete random variables were the ones which can take a countable number of possible values. And now this is the time for learning about continuous random variables. As we have said, continuous random variables are defined and conceptualized in a totally different way. So why? Because continuous random variables can take on a continuum or an uncountable number of possible values. For example, in the last week we have taught that the number of customers who enters a post office or a supermarket throughout the day is a discrete random variable, because this discrete random variable, or potentially the number of entrances that occur in a supermarket, can only take non-negative integer values, and this set is a countable set. You can count the number of elements in this set, the potential value set. However, if you focus on this example, let's just say X represents the weight of a randomly selected university student in kilograms. Now, this X value theoretically is a value between 0 and infinity, right? So somebody weighs in kilograms with a value that is from 0 to infinity. You know, the kilogram of people or a human being does not just take integer values, right? So if you have a sensitive device that measures the weight of a human being, then this value, the weight, can take any possible real value from 0 to infinity. So 0 is a theoretical lower bound. You know, nobody weighs, for example, less than 30 kilograms, of course, and nobody weighs more than 300 kilograms as well. However, this is just a theoretical boundary. So anybody's weight is supposed to be distributed between 0 and infinity. However, it can take a continuum of possible values. But why? Because the kilograms, the weight of a person, is a measurable value. You cannot count the kilograms. You can measure the weight. You cannot count the weight. So because of that reason, X can take a continuum of values between 0 and infinity. And if you remember, we have taught that any interval subset of real numbers is a uncountable set. Therefore, here X can take an uncountable number of possible values, and X is a continuous random variable. Similarly, the daily profit of a corporation in dollars is again a continuous random variable. So Y is a value between minus infinity and plus infinity. We say daily profit, but not every day the corporation is going to make a profit. On some days it is going to have more costs than the revenue. So the profit on some days can be negative as well. So we theoretically cannot put any boundary to the daily profit. And we say that it is between minus infinity and plus infinity. So when we measure a monetary unit, we do not just stick to the integers. The monetary value can take any value from minus infinity to plus infinity. And because of that reason, again, we assume a continuous distribution. Actually, when you talk about dollars, for every integer dollar that you have, in between, there is only 100 cents, right? So $1 is 100 cents, and there is not a less measure than cents when you measure the monetary unit. However, because we are talking about large amounts of money here, again, even though the values are discretized, it is possible that we assume a continuous distribution again, just like there is a continuity of the monetary value. And if T is denoting the water purity percentage, you know, the theoretical values for a percentage value are between 0 and 100. Though you are going to get a percentage value which is close to 100. However, any percentage value can be between 0 and 100, and not just integers, not just rational numbers. It can be any possible real value within this interval. Therefore, the water purity percentage is something measurable again, and it takes a continuum of values between 0 and 100. And again, this is a continuous random variable. So we need to understand at this point, discrete random variables can be defined with respect to their probability mass functions. However, if a random variable takes a uncountable possible values, how can you define probability masses to these possible values one by one? It is impossible. So because a discrete random variable can take a countable number of possible values, you can define a probability mass function. You can say that this random variable can take the value of 0 with this probability, and it can take the value of 1 with this probability. You can give a list of these probabilities. However, if the random variable is supposed to take a continuum of values, if it is a continuous random variable, how can you define these probability masses one by one for each possible value it can take? Unfortunately, you cannot. It is impossible. So the probability mass functions will not work for continuous random variables. Instead, we totally define a different concept, which is called probability density function for x. If x is a continuous random variable, we can express probabilistic information related to that random variable with a probability density function. So probability density function is going to be a very new concept, and it holds the probability information related to this continuous random variable x. Remember now, the word mass is used for discrete random variables and the word density is used for continuous random variables. And even by looking at this word, even by looking at the probability density function statement, you can understand what type of random variable that you are working with. So for example, if the question says x is a random variable with the probability mass function defined as follows, then you need to understand that x is a discrete random variable. So it should be handled like it's a discrete random variable. However, if the question says x is a random variable that follows probability density function as follows, in that case, you need to understand that x is a continuous random variable. So even with this wording, you can distinguish a discrete and a continuous random variable. Now, my friends, again, just like in the discrete random variables case, we can also compute a cumulative distribution function for continuous random variables as well. So we are going to define it. And finally, the expected value concept and the variance concept, which measures the central tendency and the spread of that random variable respectively, they can also be calculated for continuous random variables as well. So these three concepts, concept 2, concept 3, and concept 4, they are basically common concepts for discrete and continuous random variables. However, the probability mass function is going to be replaced with something new that is called probability density function. What is probability density function now? First of all, my friends, let's just assume x is a continuous random variable, and it says that x must have a non-negative function f, which is going to be called probability density function. And this function is going to be defined for all x values, all the real values, and it is going to provide us this probability. For a continuous random variable, if you want to calculate the probability of that random variable being between a and b, or in other words, the probability of that continuous random variable to be within the AB interval, if it is computed by the integration of fx from a to b, then we call that x is a continuous random variable with probability density function f. So the probability density function, my friends, is going to help us to calculate such interval probabilities by integrating that function from the lower bound to the upper bound of that interval. So you simply integrate the probability density function from a to b to calculate the probability of that random variable to be between a and b. So we call this function probability density function. If a random variable has a probability density function which helps to calculate such probabilities, then x is going to be a continuous random variable. If x is a continuous random variable, then it has a probability density function which helps to calculate such interval probabilities by the integration of the PDF from A to B. Now, just like probability mass function, as the probability mass function was abbreviated as PMF, again, there is an abbreviation for the probability density function, and it is PDF. In most of the books, the abbreviation of the probability density function is PDF. So let us give the physical meaning of the probability density function. Now, remember in the previous page, it says f is a non-negative function. So if it is a non-negative function, it is going to be a function which is either 0 or above the horizontal axis. So we have the horizontal axis here, and the PDF is going to be a function like this. It's a non-negative function, which can never take negative values. Now, if you are interested in the probability of x being a and b, then you are going to integrate the function f, just like here, between a and b. So let's move forward. It says, suppose x is a continuous random variable that denotes the amount of time in hours that a worker spends to set up a lathe machine. Okay, a lathe machine helps for shaping steel products. And every time we intend to use such machines for manufacturing, we need to spend some time to prepare this machine for the manufacturing lot. So this is called the setup time. And this setup time for this lathe machine in hours is a random duration. Now, because the durations are measurable, I mean, you can check your clock and you can measure the time. You cannot count the time. Now, this amount, this setup time, is a random variable, that is x, which can take values between 0 and 4. So the minimum amount of setup time is 0 hours. The maximum amount for the setup duration is 4 hours. And it follows such a probability density function, x over 8. So anywhere else, our function is 0. So this is a partially defined function. The function is x over 8 between 0 and 4. However, it is equal to 0 at anywhere else. The question is this: what is the probability that a worker completes the setup between 2 and 3 hours? So we are going to say that x is a random variable that represents the setup time, and the question is asking the probability of this x to be between 2 and 3 hours. So what we are going to do is we are going to calculate the definite integral of the probability density function between 2 and 3. But be careful, the function is defined as x over 8 between 2 and 3. Okay? So you always need to be cautious about the elsewhere concept as well. For example, if the question was asking, what is the probability of the setup time to be between 3 and 6 hours? Then, when you are integrating, you need to integrate x over 8 between 3 and 4. And from 4 to 6, you are going to integrate 0. Because from 4 to 6, the function is defined as 0. And it is not going to create any value, obviously. When you integrate 0, you do not get anything. Now let's integrate the probability density function from 2 to 3, and between 2 and 3, we know that the function is defined as x over 8. And if you integrate x over 8, you get x to the power 2 divided by 16. And since this is a definite integral, we need to plug in the upper bound and lower bound values, and then we are going to subtract the integrated function plugged in with the lower bound from the integrated function plugged in with the upper bound. So 3 to the power 2 over 16 minus 2 to the power 2 over 16, which will give you a 5 over 16. So the probability that the setup is going to have a duration between 2 and 3 hours is going to be 5 over 16. Okay? Now, my friends, let us draw this probability density function and see the physical meaning of the calculation that we have done. So the function is equal to a linear function which is x over 8 between 0 and 4. But anywhere else, the function is 0. So this black bold line gives us the probability density function. And the probability that the random variable is between 2 and 3 is the integral of this function between 2 and 3, which is the area of the shaded region. And because the shaded region is a trapezoid. And how do we calculate the area of a trapezoid? So we measure this height and this height, take the average of these both heights and multiply with this side of the trapezoid. And you can easily calculate x over 8. For 2, it is going to be 1 over 4. And for 3, x over 8 is going to be 3 over 8. And the average of them is going to be 5 over 16. You are not supposed to multiply it with 1 in any way. So the area of this trapezoid is 5 over 16. So without even using the integral, we can calculate this probability because of the linear function. We know how to calculate the area of a triangle or a trapezoid from primary school. So this is how we solve this problem. However, as I have told you, if the question asks you the probability of x being between 3 and 6, now you are supposed to integrate the density function between 3 and 6. However, be careful, between 3 and 4, the function is defined as x over 8. Between 4 and 6, it is defined as 0. So you are only supposed to calculate the integral between 3 and 4. Now let's move forward, and this time we are going to deal with a probability density function which does not have a practical shape, and obviously the only method that we can use will be integration. Again, there is a random amount of time in hours which represents the amount of time in hours that the computer functions before breaking down, the time that it works perfectly until the first breakdown. Obviously, again, we are talking about the amount of time here, and it is a measurable amount. It is going to be represented by a continuous random variable. So when you experiment on this, you are going to see eventually how much time that it is going to work. However, at this point, you should say that it is a random amount of time. So you do not exactly know when the computer is going to break down. And that random amount of time has the probability density function given in this form. As you can see, the probability density function defined positively for x values which are greater than or equal to 0, which means the amount of time that a computer is going to work until the first breakdown is taking non-negative real values. In fact, if I ask you how much time did your computer work before the first breakdown, you cannot say, for example, -5 years or -2 years. So it can either be positive or it can be 0 as well. I mean, you can purchase the computer and it may immediately stop working. So we say that the amount of time can only take non-negative values, and the probability density function that represents that amount of time, likeliness, is 1 over 100 times e to the power minus x over 100. So we have an exponential function here. And it is 0 elsewhere. So for negative values, there is not a density value. So it is impossible. If the density function is 0, then these values are impossible to be realized. So the question asks, what is the probability that a computer will function between 50 and 150 hours before breaking down? Now, my friends, remember, this probability density function represents the amount of time in hours. And this means in the question, if it asks me the probability that the function time to be between 50 and 150 hours, I can safely use these two values as integral boundaries. Then compute the integral, and between 50 and 150, the function is defined with this part. Secondly, for part B, it says what is the probability that it will function for less than 100 hours. So what is the probability that it will break down in the first 100 hours? The amount of time until the first breakdown will be less than 100 hours. So this time we are going to integrate the PDF from minus infinity to 100, because this interval is minus infinity to 100. However, because our random variable can never take negative values, we simply are going to integrate the above function from 0 to 100. So for the first part, I'm just going to integrate this PDF. And how do we integrate exponential functions? So 1 over 100 is just a constant multiplier. And how do we integrate exponential functions? We basically look at the interior of the exponentiation, which is minus x over 100. And this minus x over 100, it's a linear function. And because it's a linear function, we can easily integrate this. If it was a quadratic function, for example, x squared, it was impossible to integrate. Okay, but it's a linear function, luckily. So how do you integrate this? The coefficient in front of x, which is minus 1 over 100, must be taken as inverse and multiply the whole function in front of it. So we have 1 over 100, and the inverse of the coefficient at the power is minus 1 over 100. If you take the inverse of minus 1 over 100, it is going to be minus 100. And when you multiply minus 100 with 1 over 100, they will cancel out, only the negative sign will remain. So the integral of this function is minus e to the power minus x over 100. In fact, if you take the first derivative of this function, you will exactly get this. Now, you will simply plug in the values 150 and 50 here. And if you plug in 150, you get minus e to the power minus 3 over 2. If you plug in 50, you get minus e to the power minus 1 over 2. With a subtraction operation, their difference will give you the probability. For the first part, it is minus 0.2231. And for the second part, we have minus 0.6065. However, the minus sign between these two functions makes it a plus, and the result is 0.3834. Now, the probability of x being less than 100. To calculate this probability, I'm just going to integrate the probability density function between 0 and 100. Actually, this event, the probability that the computer will break down before 100 hours, means an integration from minus infinity to 100. However, because the PDF is defined as 0 from minus infinity to 0, we are just integrating this part. So we integrate this from 0 to 100. Again, the integral of this PDF is the same as above, but this time we are just going to plug in 100 and 0 values. When you plug in 100 value, you get minus e to the power minus 1. And when you plug in 0 value, as you know it, e to the power 0 is always 1. Therefore, you need to subtract minus 1 from minus e to the power minus 1. And because of this minus sign, this minus 1 becomes plus, and 1 minus 0.3679 is 0.6321. You are supposed to calculate this exponential function using a scientific calculator. So, just like the probability mass function, there are some common and important properties of a probability density function as well. First of all, I have already stated this, but a probability density function is a non-negative function. Why? Because of the axioms of probability. You know, according to the axioms of probability, you can never define a negative probability. And if you cannot define a negative probability, then the probability density functions are supposed to be non-negative functions as well. Which means for all real values x, the probability density function of a random variable is supposed to be greater than or equal to 0. And another concept is this. You know, if I ask you for a random variable, either discrete or continuous, the probability of that random variable to be between minus infinity and plus infinity, it is supposed to be equal to 1, right? Because based on what we have learned so far, random variables can only take real values, and therefore the probability that a random variable to be between minus infinity and plus infinity will be automatically equal to 1. And how do you calculate this probability? By integrating the PDF from minus infinity to plus infinity, obviously. And if this probability is equal to 1, then this means the total area under a probability density function must always be equal to 1. Please remember this. The total area under this probability density function must always be equal to 1. For example, let's check this triangle. What is the area of this triangle? So the height of the triangle is 0.5 and the base is 4. So 4 times 0.5 is 2, and you divide it to 2, you get a 1. So the area of the triangle, the area under the probability density function is equal to 1 here. I mean, if you integrate this function from 0 to infinity, again, you are going to get a 1. So this is the golden rule, my friends. The total area under a PDF, the integral of the PDF from minus infinity to plus infinity will always be equal to 1. And another important fact about continuous random variables that you need to understand at this point is, if you are interested in calculating the probability of a random variable to be equal to a value, okay, then you are supposed to integrate the PDF between A and A. If this value is A, then you are supposed to integrate the PDF from A to A. Obviously, this integral will give you a 0. Because of that reason, we should say that for a continuous random variable, the probability of it to be equal to a specific real value is always assumed as 0. Which means for continuous random variables, we can only talk about the interval probabilities. So because of this fact, because when you integrate a continuous function between two boundaries which are the same, and this value is going to be equal to 0, we can never speak about the probability of a continuous random variable to be equal to a specific value. For example, if I ask you this, what is the probability of a random student to be exactly 78 kilograms? You cannot talk about this probability because nobody is exactly 78 kilograms, because it is impossible to test that. I mean, it is impossible for you to prove it. When you measure your weight, obviously you'll see some rounded numbers on a digital device. The digital device will tell you you are 78 kilograms. However, it is just rounding it up. It is not actually 78. Nobody is exactly 78 kilograms. Or you can never prove, for example, if you want to keep the timing for 1 minute, nobody can exactly keep a time for 1 minute. For example, you are measuring the time until somebody enters in your room. Right now, you start measuring the time and you are measuring the time until somebody enters in your room. Even if you measure it, you actually think that you measured it, because you are going to observe first that somebody enters the door from the door, then you are going to check the clock. Okay, and there will be some time between these two events. Because of that reason, for the continuous amounts, we can never talk about the equation probabilities. Instead, we can only talk about the probability of a continuous random variable being in an interval. And because the equations, they do not have any specific probability, they have 0 probability, this probability, the probability of x being between A and B, where A and B are included, and this probability, the probability of x being between A and B, where A and B are not included, are exactly the same. So this probability, even if we have inequality here, and if we have strict inequality here, the probabilities are going to be the same, because both of these probabilities, both this one and this one, will be calculated by integrating the PDF between A and B. Okay, even if these A and B here are included, are not included, it doesn't matter, because the equations have 0 probability. Or if the probability for a continuous random variable is between A and B, where A is included and B not, or A is not included and B is included, again, you are going to get the same result. However, my friends, please remember, this is not true for discrete random variables. For a discrete random variable, this probability and this probability may be different, because there may be a probability mass at A or B. So for the discrete random variables, this is not true. Only for continuous random variables, Whether you have an inequality sign or a strict inequality sign, it doesn't matter. You are always calculating the probability by defining this as a lower bound and upper bound. Now we are going to solve a question related to continuous random variables again. Suppose that x is a continuous random variable that follows the probability density function. And here's the case. This random variable has the probability density function fx. And by the way, my friends, if you have realized, I was using letter P for probability mass functions of discrete random variables, but this time for density functions, I am using F. For probability mass functions, we never use letter F, and we use this letter F for probability density functions. Now, according to this probability density function, the random variable x can only take values between 0 and 2. And elsewhere, the PDF is equal to 0, which means this random variable can take real values between 0 and 2. In fact, 0 and 2 are not included as it seems, but it doesn't matter. I mean, even if you include them or do not include them, it doesn't matter because you cannot talk about the probability of x being equal to 0 or x being equal to 2. In fact, you cannot talk about the probability of x being equal to 1 as well. I mean, x cannot be equal to 1 because you cannot prove it. However, what you can prove is this. I mean, when you measure x, you can prove that it is either less than 1 or greater than 1. So you can prove that it is between two values. However, you cannot prove that it is exactly equal to a value. Now, the question starts with this. What is the value of c? So you see the PDF is defined. However, there is an unknown value c here. So the PDF is defined as a function of x, but there is an unknown value c here. How do I calculate c, my friends? Again, we are going to use a similar analogy that we have learned from probability mass functions. Remember, the important property of a probability density function is that the area under the PDF will always be equal to 1. So we are going to integrate this function between 0 and 2, and it is supposed to be equal to 1. And we are going to determine the c value for which this integral is equal to 1. So we integrate c times 2x minus x squared. C is a constant, so all we need to integrate with respect to x, 2x and x squared. The integral of 2x is x squared, as you know it. So you increase the power by 1. You divide the multiplier in front of x to that number. So x becomes x to the power 2, and you need to divide 2 to 2, and they will cancel out. And similarly, minus x squared, when it is integrated, it becomes x to the power over 3. So you increase the power by 1, and you divide that function to that value, 3. Now, let's plug in the lower bound and upper bound values and make the subtraction. When you plug in 2 here, you get 2 minus 8 over 3, which is going to be 4 over 3. And there is c here, do not forget about that. And when you plug in 0, you simply get a 0 from that function. Therefore, the difference is going to be 4c over 3. And if this is going to be equal to 1, if the area under the PDF is going to be equal to 1, then c is equal to 3 over 4. C is supposed to be equal to 3 over 4. Now that we have determined the constant c, we can rewrite our probability density function as in this form. Now we can solve the further questions. If we go back in part B, the question asks the probability of x being greater than 1. And in order to find the probability of x being greater than 1, all you need to do is to integrate the PDF from 1 to infinity. From 1 to infinity. However, remember, our function is equal to this positive function between 1 and 2. However, above 2, the function is 0. So there is no necessity to make this calculate all this integral. All we need to calculate is the integral of the positive function between 1 and 2. And when you integrate this function, you get 1 over 2 as a result of the integral. So that's it basically. So you need to calculate the integral of the PDF and plug in the values 2 and 1. And this is going to give you the area under the PDF between 1 and 2. And actually our PDF here is this. So remember the PDF 3 over 4 times 2x minus x squared. And you can easily see that this function is this. 3 over 4 times 2x minus x squared. When you draw that function, you will easily see that it is going to be a quadratic function, second order polynomial function, between 0 and 2. And at anywhere else, the function is 0. And the question is asking us the probability that x being greater than 1, which is the area under the PDF on the right-hand side of one value, which is 0.5. Why? Because the function here is symmetric around 1. If you draw the PDF without any necessity for taking the integral, you can easily understand that because the function is symmetric around 1, the area on the right-hand side of this 1 should be 0.5, whereas the area on the left-hand side, this white area, should also be equal to 0.5. So you can also say that the probability of x being less than or equal to 1 is also 0.5. In fact, you can also find it as the complement probability, right? I mean, if you know that this probability is 1 over 2, you can also determine the probability of x being less than or equal to 1 as 1 minus 1 over 2. Because we know from the first proposition of probability, the complement events probability can always be found by subtracting the original events probability from 1. Okay, and the final question is a simple question. What is the probability that x is equal to 1? Remember now, for continuous random variables, for a random variable to be exactly equal to a certain value has the probability of 0 always. The thing here is this. The event x being equal to 1 is improbable. So there is no positive probability for that. It is improbable. However, it is not impossible. At some point, x can be realized at 1. Anything between 0 and 2 is possible. For this random variable, anything between 0 and 2 is possible. However, this is improbable because the probability must be equal to 0. So this is the difference between improbable things and impossible things. It is because of the continuity of the values. You can in fact prove this by integrating the PDF from 1 to 1, and you will definitely get a 0 from that integral.